Hello and welcome to the annual Department of Mathematics Awards ceremony. Typically, we would gather in the Psych Auditorium at East Hall to celebrate your accomplishments, but thanks to COVID-19, that's not going to happen this year, and instead you get to join us in our various living rooms, and libraries, and dining rooms, and also witness how much hair we've grown since this all happened, and since we can't actually get out to a barbershop yet. My name is Stephen DeBacker, and I am the Master of Ceremonies for this event. So a brief outline of what will happen. We'll begin in just a moment by giving the parents and friends of the students who are being awarded a taste of what it's like to be a student in a math course at the University of Michigan. And then we'll proceed with the awards, and that will be it. So, but before we begin, I have to thank all of the members of the committee. There are now over 650 math majors, and so that makes deciding who will win these awards very challenging. In the old days, when there was only 120 of you, it wasn't so hard, but now it's actually pretty darn difficult. And so I thank the committee, whose members include Jinho Baek, Dan Burns, Christina Cherto, Lijun Ji, Jeff Legarius, and Roger Natarajan. I especially thank Christina for putting together this excellent video. So we're going to begin by giving you a taste of what it's like to be a student at the University of Michigan. And our speaker today is my colleague, Professor Jinho Baek.
So my name is Jinho Baek. I'm a professor at the math department. So I'm going to talk about Pineless equations. This is certain type of nonlinear differential equations. The reason that I'm choose to talk about this one is that the story related to Pineless equations. This contains a lot of aspects. The first one is that there's a story about the interesting career of a mathematician. Also, it contains two important mathematical thinking or ideas. One is that instead of focusing on one particular problem, mathematicians tend to study all problems as a whole thing and then classify them. And another aspect of mathematical thinking is that sometimes we start from the solutions rather than problems, solutions and properties, and then try to find out what kind of problems lead to that kind of solutions. Okay, so we kind of go backward and combine with the first one, we then consider all problems and we already classified them. So if some other problem can show that that belongs to one of those list of the problems that we considered, then we get those properties automatically. And also in this story of Pineless equations, it's a story about interesting mathematical research was neglected for a long period of time, but then later it was revived and turned out to have connections to many interesting connections to other areas. Okay. So let me get started. So I'll start with first order linear differential equation, something like y prime equals 2y. You learned in high school, probably, how to solve this equation. It's given by y is equal to constant times e to the 2x. In the college, in the university, that you learned how to solve second order linear differential equations, something like y double prime plus 6y prime plus 5y equals 0. So you learned it may be math 216, 286, or 316. That the general solutions are given by C1 e to the minus 3x plus C2 e to the minus 2x, where C1 and C2 are arbitrary constants. And these are the only solutions, and all solutions can be written in this form. It shows several properties. For example, the space of solutions, we collect all of them. That's a space of functions. That forms a two-dimensional linear vector space. And all solutions of the equation of the type that second order linear differential equation, homogeneous and constant coefficient. All solutions are elementary functions given in terms of exponential, in our case here, or trig functions, or polynomials. And furthermore, this is an important point that will be relevant to our next page, that all solutions are smooth, they are differentiable, they have no singularities. Right. Now this was a second order linear differential equations. In these classes, we touch upon a little bit of nonlinear differential equations in the first order, but second order nonlinear differential equations, we rarely touch them because it's hard to solve them. There's no systematic way of doing it. Let's think about that a little bit. So the general nonlinear differential equation, second order of the form, that can be turned into form y double prime is some function of x and y prime. So let's have a few examples. Example 1, the first example. The solution, you can check that if you plug y equals ln of x minus x naught for arbitrary x naught, if you plug that into the equation, it can show that it solves the equation. So this ln function are solutions. They are not the only solutions. There could be other solutions, but this one gives you a solution. And note that this function, solution has now singularity. It's not well defined and x equals x naught. And the singularity depends on our initial condition. The second example, the solution is, in this case, some solutions are given by 1 over x squared minus x naught squared. This one also has singularity, but this time it's not the log type singularity, but rather in complex analysis called pole singularity. Example 3, this is a Bessel equation. This is a linear second order, but still equation has this must be studied in 2016 to 86 to 2016, that the solutions are allowed to have singularities. So solutions will have singularity, most of them, and then they will have a singularity at x equals 0. X equals 0 coming from that the coefficient in front of x, y double prime. All right. Okay. So so in this case, note that in example 3, the singularity is 0. That location does not depend on the initial condition. Whereas in example 1 and 2, singularity is at x now, which is an arbitrary point, which is determined from the initial condition. Okay, so two things can happen. So the story about the Pineless is that in 1900 to 1910, so more than 100 years ago, Pineless was a mathematician. He considered the following problem. So you consider all differential equations, right? So it's not only one single differential equation, but all y double prime is equal to f of x, y prime under the following conditions. The one is that the function f should be a rational function. Then the previous examples are all rational functions. Y double prime equals a rational function of x, y prime. Second condition, which is nowadays called Pinellas property, is that the solutions are allowed to have singularities, but if it's a log type singularity, that singularity location should not depend on the initial condition. If it's a pole type singularity, then the location of the pole type singularity are allowed to be depending on the initial condition. So it's some kind of condition that are imposed, which the idea is to generalize the class of functions which have the property of linear differential equations, but expand it more to nonlinear differential equation case. What Pinellas did, and then later completed by Cappaert, who was a student of Pinellas, was that they tried to classify all such differential equations. So one can imagine that if you have one solution, one differential equation, if you do the change of variables, you replace x by, I don't know, x e to the x, and y by another thing like y squared plus y prime or something like that, the one equation look quite different from the second, the new variables. So, but those two things are equivalent. So after suitable changes of variables in either both or either of x and y, one can differentiate various equations whether they are transformed to another among the equations that satisfy the Pineless properties. And it turned out, when they worked this out, they were able to reduce all the differential equations into just 50 equations. So they wrote them all down and then check one by one. By looking at the list, 44 of them turned out to be previously known equations. Those are the ones that can be solved by elementary functions, trig, exponential, or polynomials, or rational functions, or some other classical special functions such as Bessel functions, Wentzel equations, Airy equations, and those things which are well studied in 19th century. And that left 6 nonlinear equations they could not reduce to anything else. And then that was the story. Okay. So those 6 left equations, nowadays they are called Pineless equations, P1 through P6. There are some examples there. The equation becomes quite complicated, especially P4, P5, P6. P6 becomes quite complicated, nonlinear equations. And there the alpha or beta, gamma, delta, they are constants. So as P1 actually has continuum of equations depending on your parameter alpha. So that was the end of the story. So that's the story of Pineless. Can be classifying the problems. So this one has this pure mathematical interest. There are some properties that we want to impose. So in other words, we want to impose some properties or solutions, and then they constructed all equations. And then doing so, they did not think about one equation, but thought about all possible equations, and then classify all of them. That's very interesting. Okay, but that is completely forgotten once that work is done. Okay, for a long period of time. I'll come back to that, and then how that was revised and how it's impacting these days. But let me just talk about Pineless himself. So Paul Pineless was a mathematician. He worked in differential equations, as the Pineless classification indicates. He was also interested in aviation theory, which was happening at the moment. That's turn of the 20th century, where indeed he was the first airplane passenger of Wilbur Wright in France back in 1908. But then, after all this mathematical work, he changed his career. He became a politician. He was a Ministry of War or Air or several different things, but eventually became a Prime Minister of France during several months in 1917 and also several months in 1925. Right, so this interesting career change. So many of you graduating students, some of you will continue doing mathematics, but some of you will be doing something else. But I think it's important that you do variety of different things. Lots of people in lots of line of work have a mathematical background. I think that's going to be a very, very important thing, and something like politicians or other things, including. All right, so back to the mathematical theory. So as I said, around 1910 and 1990 and 1910, there's this beautiful classification theory, but it was completely forgotten. Okay, there are a few works, of course, but there's not much of use of it. But then, in 1976, physicists Wu, McCoy, and Tracy and Baruch was studying something called 2D Ising model, which is a statistical physics model. They arrived at some equation in the end, and then they realized, I don't know how they realized, but they realized that that is given by one of the Pineless equations, Pineless 3. So boom, so people now got to have one example that interesting mathematical physics problem or statistical physics problem or statistical problem can be written in terms of Pineless equation. Once that is out, then people started to realize many other things can be written in terms of Pineless equations. So in 1980s, for example, Bohr's gas, that's another physics problem, was realized to be related to Pineless 4. That's Jimbo, Miyamori, and Sato's result. Okay, maybe Pinellas 5. Sorry, Pinellas 5, and also many integrable partial differential equations, such as KdV equations, found out to have a reduction, and then the reduction satisfied Pinellas equation. And then through the 1990s and until now, the last 30 years, many things, including random metric theory, including subsequence problem of random permutations, random tiling, isosceles random walks, and random growth models, interacting particle systems, and KPG equations are related to Pinellas equations. So here are some examples. So top left picture, that is a histogram of eigenvalues of 2000 by 2000 random Hermitian matrix. Take Hermitian matrix, big matrix. Entries are independent random variables given by Gaussian. Then you'll have 2000 eigenvalues, real eigenvalues, and you put a histogram. If you look at the largest eigenvalue and then compute something I wrote up there, which is take the log of the probability that the largest eigenvalue is less than or equal to x, take a double derivative with respect to x, and call it u of x. Then one can show that this u of x satisfies Pinellas 4. It's not an obvious computation at all, but it is known to be the case. The next picture shows that the non-intersecting Brownian motions, and that is related to Pinellas 5. And the top left corner is a picture of random tiling. So if a hexagon, you take this rhombi and then fill it, and there are many ways of doing so. So you look at all possible ways you tile. You just pick one tiling randomly, and this is a typical picture like that. You can see that there are 6 corners which are frozen in the middle. There's temperate mixed part. So there's a boundary which we call the Arctic boundary. The Arctic boundary has certain fluctuations because it's a random thing, and in the large or small rhombus size limit, the fluctuation of this boundary is related to Pinellas 2. In the bottom right-hand side, ignore the left picture, but the right-hand side picture, there are lots of gaps inside, and that is a random growth process. So there's something is growing in a certain way, such a way that you can think of like growing of Tetris in the game. So if you are just overwhelmed by the speed, and then they are all just popping down from the sky, and then just goes up very quickly, that there are all these holes inside. In that case, the fluctuation of the height is expected to relate it to Pinellas 2. This is not proven because it's a related model is proven. This particular model is not proven. So anyhow, so this is the story of the Pinellas, which is studied in this pure classification problem and completely forgotten in the middle, but then revived through this new exciting connection to many other things. Okay? And I, for example, work in some of these connections these days. All right, so congratulations to all graduating seniors. I hope that you had a good time at the University of Michigan and Math Department, and I hope that you learned something. And I wish you all the best.
Thank you, Jinho, for that excellent talk. We now enter the part of the award ceremony where we actually present the awards. And our first presenter will be Professor Jinho Baek.
I'd like to present Frank Raymond Award in Geometry and Topology. Frank Raymond is an alumnus of Michigan. He completed his PhD at Michigan under the direction of Raymond Wilder in 1958. He was serving as a junior faculty member at the Institute for Advanced Study at the University of Wisconsin. He returned to Michigan in 1962. Since 1997, he has served as an emeritus professor of mathematics. He made many contributions in the areas of algebraic and geometric topology, particularly in the study of Seifert manifolds, as evidenced by more than 25 PhD dissertations he directed in his many co-authored papers. He delighted in working on math problems with others. This year's winner is Ifan Lu. So congratulations, Ifan. Next award is Jack McLaughlin Award in Algebra. Jack McLaughlin, 1923 to 2001, spent his entire professional career at the University of Michigan. He made many contributions in algebra, particularly in the area of finite group theory, relative theory, and commutative algebra. Paul Halmos, a European colleague, once remarked that there are a number of ways to tackle a mathematical problem, but when all else fails, ask McLaughlin. During his 44 years of teaching, he played a very active role in the undergraduate program, and he was considered an excellent and demanding teacher, especially of honors students who sought out his courses to measure their ability. His prize is given to an undergraduate student who excels in the study of algebra. This year's winner is Alexander Wang. Congratulations, Alexander. Next award is George Piranian Excellence in Mathematical Writing Award. George Piranian, 1914 to 2009, served on the Michigan Math faculty from 1945 until his retirement in 1983. He was a very active researcher in the area of complex function theory, was particularly well known for his ability to generate counterexamples. He was deeply involved in the honors program. He advised honors students both at the mathematics and college level. He was the editor of the Michigan Math Journal for 20 years. During his tenure at the journal's Helm, he became known far and wide for his exceptionally high standards for both mathematics and exposition. He turned what was a floundering journal into the respected journal it continues to be today. Indeed, many awards, including this one at today's ceremony, are funded by the journal. This year's award winner is Zachary Luallen. Congratulations, Zachary.
The next set of awards will be given to students who have done particularly well in various mathematical competitions. And the presenter for these awards is Professor Dan Burns.
Hi, my name is Dan Burns, and I'm here to honor the winners of the various math competitions that our students have participated in this year. And these are the Putnam competition, the UM Undergraduate Math competition, and the Virginia Tech Regional Math competition. It's quite a spread of difficult exams and difficult competitions. So the Putnam is the grandparent, or the granddaddy, as we might have said, of all these competitions, at least in this country. And it's always an honor for our students to do well there. I'll read the citation about this year's winners from Michigan. So it says the 80th Annual William Lowell Putnam Mathematical Competition. It's a rigorous 6-hour, 12-question exam, which tests the originality and technical competence of math students. There are 4,229 students from 570 institutions in the US and Canada who participated in this year's Putnam competition. And of those 570, our team ranked 25th. And the winners this year, the local winners for best performance, are Xijian Cheng in first place, Posun Wu in second place, and Stephen Jessina in third place. Congratulations to the three of you. That's quite an accomplishment, actually. That's a very difficult challenge. So the 37th Annual University of Michigan Undergraduate Mathematics Competition. Now, this competition is much younger than the Putnam, and it's our local contest, which is nevertheless pretty eagerly contested. So we're always proud of the winners of this competition around the department. And the citation says that the competition was held on April 4th, when 22 University of Michigan students participated in solving a problem put forth by the Undergraduate Competitions Committee. And the winners, these top three students tied for first place. So there were three who did very well and tied for first. And they are Ramchandra Apte, Youngwoo Kwon, and Dinghao Chen. So once again, congratulations to the three of you. And finally, not much older than our own competition is this Virginia Tech regional contest. And this is a shorter exam than the Putnam and is widely taken, but over a smaller geographical region than the Putnam. And success in this contest is always gratifying to all of us here at Michigan. So the citation for this year's winners: 41st Annual Virginia Tech Regional Mathematics Contest. This contest began in 1979 and has grown to the point where over 100 schools with over 700 contestants participate in a typical year. Contestants at each participating school take the 2.5 hour exam. So locally, the winners are, again, it's a tie. 5 students did extremely well, and it's a tie between them. And they are Bohan Xu, Connor Novak, Kyu Hyun Park, Yu Bing Kui, and Martin Pena. And again, congratulations to all 5 of you. Well, those are the results for the competitions this year.
As your master of ceremony, I should occasionally insert a joke. So here's a vaguely mathematical joke. What did the parrot say when she escaped from her cage? Polygon. The next presenter is Professor Jeff Ligarius.
The William Levesque Award in Number Theory. William J. Levesque, who lived 1923 to 2007, was a professor in the University of Michigan Math Department for 22 years. He made many contributions to the study of number theory, particularly in the areas of transcendental numbers, uniform distribution, and Diophantine approximation. Recognized by his colleagues as an effective administrator, during his career he served as Executive Director of Mathematical Reviews, Chair of the Math Department from 1967 to 1970, and Executive Director of the American Math Society from 1977 to 1988. During his time at Michigan, he played an active role in the Mathematics Honors Program. This award is given to an undergraduate who excels in the study of number theory. This year's winner is Feng Chen. The award also includes a mathematics book written by Levesque called Fundamentals of Number Theory, which we will give you when the opportunity permits. The Wilfred Kaplan Award in Applied Mathematics. After receiving his PhD from Harvard, Wilfred Kaplan, who lived 1915 to 2007, joined Michigan in 1940 and remained here until his retirement in 1986. His research encompassed the topological behavior of solutions of differential equations, complex function theory, and applied mathematics. He wrote many textbooks, particularly one in advanced calculus. Some are still in use, and was a fantastic and well-loved teacher. His co-author and colleague Don Lewis commented that, first and foremost, Wilfred Kaplan was a teacher. He enjoyed conveying the beauty and usefulness of mathematics, and his students responded enthusiastically. He was a superb expositor, and his ability to elegantly convey mathematical ideas explains the enormous impact of his textbooks. This prize is given to an undergraduate who excels in the study of applied mathematics. This year's award winner is James Hazelden, the Sumner B. Myers Award in Analysis. Sumner Myers, who lived 1910 to 1955, arrived at the University of Michigan in 1936 and remained here until his untimely death. He made many contributions in the areas of analysis, differential geometry, and topology. He was well respected by both students and younger faculty who sought him out for his wise counsel on both mathematical and personal problems. As a teacher, he has been described as magnificent. In his lectures, he knew how to stimulate students, and outside of lectures, he was generous with both his time and his copious mathematical talent. This prize is given to an undergraduate student who excels in the study of analysis. This year's winner is Annie Shu. I'd like to say also that Sumner Myers trained several graduate students to the PhD, and he had two who were very well known afterwards. Leonard Jimmy Savage is the most well known.
The next series of awards are given to students in the actuarial field, and they will be presented by Professor Roger Natarajan.
Hello, my name is Roger Natarajan, and I am the Actuarial Program Director at the University of Michigan. I am here to award the D.W. Simpson Award for this year. Forbes magazine selected D.W. Simpson as one of the 2018 best executive recruiting firms. They help University of Michigan in placing our actuarial students for entry-level jobs. D.W. Simpson has been partnering with the University of Michigan to award one actuarial student per academic year. D.W. Simpson awardee must be in the junior year of undergraduate study in actuarial math, must have GPA of 3.4 or better in actuarial math, and overall GPA of 3.0 or better, must have passed at least one actuarial exam, and must be eligible to work in the United States. The winner of this year's D.W. Simpson Award is Ramana Ramanathan. Ramana is a junior majoring in actuarial math and double minoring in business administration and economics. He has already passed 4 actuarial exams. He did his sophomore internship at Jackson National and planning to do his junior summer internship at Willis Towers Watson. He was a recipient of Margaret Huntington Memorial Prize in 2018. Please join me in welcoming Ramana Ramanathan. I am here to award the Irving Wilson Award. Irving Wilson received his BA in mathematics in 1950 from the University of Michigan. He was an actuary and served as the executive vice president at Phoenix Mutual Life in the Hartford office from 1965 until his unexpected death in 1981. His favorite joke was, "What is the difference between an actuary and a computer? A computer has a heart." Obviously, the joke was wrong. Irving Wilson was loved by many, and this award was funded to perpetuate the memory of how this actuary touched so many lives for the better. This award was established from memorial gifts from family and friends, as well as the Phoenix Mutual Life Insurance Company. This award is given to a student with academic excellence and promise who intends to complete the actuarial mathematics degree at the University of Michigan, has at least one term of undergraduate work remaining, has shown substantial promise of professional actuarial achievement through academic accomplishments, and participated in employment and/or extracurricular activity. There are 2 winners in this year's Irving Wilson Award. They are Mark Cappaert. Mark is pursuing a dual degree in actuarial math and business administration. He has passed the first 2 actuarial exams. He did one summer internship at Haggerty. He served on the board of SAM, which is our student club, student actuaries at Michigan. He served as the vice president in the current year and will be serving as the president for this upcoming academic year 2020-21. The second winner is Ishpreet Kohli. Ishpreet just completed his junior year. He is double majoring in actuarial math and computer science and minoring in economics. He has passed the first 4 actuarial exams. He did a summer internship at Jackson National last year and will be doing his internship at Etna this year. Please help me in welcoming Mark Cappaert and Ishpreet Kohli. Thank you. I am here to present Margaret Huntington Prize in Actuarial Research. My predecessor, Lord Huntington, established this prize in memory of his beloved mother, Margaret S. Huntington, to call attention to careers in actuarial science and the mathematics of risk. Qualifications for this award include completion of a first-year calculus course in last fall with a high grade, completion of a questionnaire, and submission of a short essay on the role of actuaries in today's society. We normally pick about 10 to 12 awards each year, and we hope these awardees will declare actuarial math as their major in the upcoming academic year. The winners of this year's Margaret S. Huntington Prize are Joseph Bednar, Ahmad Shamoud, Hannah Coles, Heyu Du, Adam Erbs, Blake Jordan, Andy Lee, Jonah Nan, Aman Saxena, David Williams II, Zhuyu Zhu, Raina Zwolinski. Please join me in congratulating these 12 award winners. Thank you. I am here to present this year's Cigna Awards. Cigna is a health services company that believes in creating a better future for its customers, patients, and co-workers. The actuarial program at the University of Michigan and the Actuarial Executive Development Program at Cigna have a close working relationship dating back to several years. The Cigna Awards are made possible from funds provided by the Cigna Foundation of Hartford and Philadelphia. The Cigna Actuarial Awards are given to freshmen and sophomores considering an actuarial career in the health insurance industry who demonstrate and exemplify the qualities that actuaries need to be successful. The prize is given to students with a minimum GPA of 3.2, completion of 1 or more actuarial exams, outstanding analytical and problem-solving talent, high motivation and demonstrated leadership qualities, demonstrated business acumen, ability to communicate both actuarial and business concepts, a one-page essay on an actuarial health insurance industry topic. The winners of this year's Cigna Award are Raina Zwolinski. She is a freshman who has completed 1 actuarial exam. She will be serving as the Casualty Actuarial Society Ambassador for the University of Michigan for this upcoming year 2020-21. The sophomore award winner is Trevor Kelterborn. Trevor is a sophomore who is triple majoring in actuarial math, statistics, and cognitive science. He has passed the first 2 actuarial exams. He will be serving as the vice president of our student club SAM, which stands for Student Actuaries at Michigan, for this upcoming year 2020-21. The second recipient of the sophomore award is Logan Driscoll. Logan is a sophomore and he has passed the first actuarial exam. Please join me in congratulating Raina, Trevor, and Logan. Thank you. I am here to present the KPMG Award this year. We are very thrilled that KPMG is establishing a KPMG Award in Actuarial Excellence for the first time. This award is designed to encourage actuarial students to consider non-traditional roles. This award is given to a student who is a junior majoring in actuarial math with a minimum GPA of 3.0, completed at least one actuarial exam, must be a US citizen or a permanent resident, has to complete 2 separate essays. The winner of this year's KPMG Award in Actuarial Excellence is Shankar Prabhu. Shankar, who just completed his sophomore year, pursuing dual degrees in business administration and actuarial math. He has passed the first 2 actuarial exams. He did one internship with Aetna during the freshman summer and will be doing an internship with Lyft during this upcoming sophomore summer. Please join me in congratulating Shankar Prabhu. Thank you. I am here to present the Natarajan Family Award. This award was established by the Natarajan family of 3 actuaries to recognize an undergraduate student majoring in actuarial mathematics who shows promise of future actuarial leadership ability, evidenced by having already assumed leadership roles on campus within the community. The winner of this year's Natarajan Family Award is Diyara Bissembayeva. Diyara is a senior, double majoring in actuarial math and data science and minoring in business administration. She served on the SAM board as career chair in the most recent academic year. She was a mentor and a member of the Outreach Committee for Girls in Electrical Engineering and Computer Science. She also served as an employer relations ambassador with the Ross Career Development Office. Please join me in congratulating Diyara Bissembayeva. Thank you very much. I am here to present the Otto Richter Memorial Prize for this academic year. Otto Richter was a 1923 graduate of the University of Michigan. He went on to become a triple fellow, Fellow of the Society of Actuaries, Fellow of the American Institute of Actuaries, Fellow of the Casualty Actuarial Society. He spent his entire career at AT&T. He was one of the earliest corporate actuaries with extensive background in the design of the retirement systems. He died in 1959. This prize is given to a graduating senior who has shown the greatest achievement in the study of actuarial mathematics, as evidenced by passing of the actuarial professional examinations, submission of a short essay on the role of actuaries in today's society. The prize was established in 1997 by a gift from the estate of Marian Richter. The winners of this year's Otto Richter Prize are Brad Pineless. He is pursuing dual degree in business administration and actuarial math. He has passed the first 5 actuarial exams. He completed 3 summer internships, served on the SAM board for 3 years as president in the most recent year. He was the recipient of the Wilson Award in 2019. The second winner of this year's Otto Richter Prize is Kira Feng. She pursued a double major in data science and actuarial math. She has passed the first 5 actuarial examinations. She has completed 3 summer internships, served on the SAM board for 1 year. She was the recipient of D.W. Simpson Award in 2018. Please join me in congratulating both Brad Pineless and Kira Feng. Thank you.
The next batch of awards will be presented by me, Stephen DeBacker. So let me go change into a different tie, and I'll be right back to do that. The Evelyn O. Bissembayeva Award. This award is given to undergraduate students who show promise in mathematics deserving of recognition and encouragement. Evelyn Bissembayeva was a 1933 alumna of the university. She did not major in mathematics, but took many math courses and later taught math at Michigan State. She was a certified public accountant and maintained an office in Ann Arbor for many years. The Bissembayeva Awards were established through a bequest by Irene Bissembayeva-Bendler, the sister of Evelyn Bissembayeva. The Bissembayeva Awards are my favorite award at this ceremony for two reasons. The first is that they are designed to encourage students to take more math. And the second reason is that here we have Evelyn Bissembayeva, a student who took many math classes but wasn't actually a math major, and she endowed, or rather her sister endowed, this award for y'all. I'm very much looking forward to seeing how much you, as math majors, can do to encourage future students at the University of Michigan to take more math. The awardees for the Evelyn Bissembayeva Award are Junshan Chen, Ethan Cohen, Parmita Devarmanesh, Chenshi Gu, Scott Guest, Jack Haviland, Zukun Jia, Andrew Kiesling, Yilin Lee, Andrew Nagoyan, Marissa O'Gara, Ananya Sridharan, Haonan Swin, and Wendy Wang. The Leon P. Zukowski Award. Lee Zukowski was an administrative staff member in the Department of Mathematics for over 25 years. Dedication, enthusiasm, and meticulous attention to detail were the hallmarks of Lee's work. Additionally, Lee served as a tutor in the math lab in the department, and after he retired, he continued to serve as a tutor and also to tutor in the English as a second language program. He also served as an officiant at many of the ceremonies, such as weddings, for various faculty members. This award recognizes the student whose work in the math lab best carries on Lee's tradition of dedication and responsibility. This year's winner is Michael Henry Selmer Wentzel. The Donald J. Lewis Mathematics Merit Scholar Award. The Michigan Mathematics Merit Scholar Award was established to honor graduating mathematics concentrators who have been recognized through merit awards and mathematics scholarships and are deserving of recognition for the excellence and consistency of their work in mathematics courses. The award is named for Donald J. Lewis, who served as chair of the math department for over a decade before moving on to be the head of the Mathematical Sciences Division for the NSF, and then coming back as a faculty member at Michigan in Ann Arbor. This year's awardees are Yushan Bao, William Garland, Natalia Genuine, Luke Kiernan, Sean Russell, Jared Stolov, Shuju Zhang, Stephen Zhou. The Marilyn and Stuart Gloyer Award. This award recognizes outstanding students of mathematics who intend to become secondary school teachers. The scholarship has been made possible by a generous contribution from Marilyn and Stuart Gloyer. Marilyn Gloyer is an alumna of Michigan. She received her bachelor's degree in mathematics in 1966. Stuart Gloyer is an alumnus of Michigan as well, and he received his PhD in chemistry. This year's awardee of the Marilyn and Stuart Gloyer Award is Joseph Meston. The Louis Zook Levy Award. This award is given annually to an outstanding graduating senior majoring in mathematics who will pursue a teaching career in K-12 mathematics. This year's award winner is Alexander Cepo. The final set of awards to be awarded at this ceremony will be given out by my boss, the chair of the department, Professor Tony Block.
Hi, I'm Tony Block, chair of the math department. It's a pleasure to be with you today at this awards ceremony, and I'd like to congratulate everyone on their achievements here at Michigan and to wish you all the best for the future. So I'd like to mention a few of the awards that I'm presenting. So the first one is the Outstanding Achievement in Mathematics Award. This award is given to graduating seniors who are deserving of recognition for excellent and consistent work in their mathematics courses and contributions to the study of mathematics in Michigan. This award is made possible with gifts from various alumni and friends of the department. This year's winners are Jun Chung An, Jen Lee Chung, Jeremy De Silva, Shijie Lee, Yu Cheng Lee, Charles Liberato, Yang Fan, Colby Keln, Sophie Hurahan, William Newman, Suzanne Sheng, and Justin Voorhees. Next is the Mathematics Alumni Scholarship. The Alumni Scholarship was established with a solicitation in 2003 of all mathematics alumni. The scholarship is intended to support outstanding, deserving mathematics students. This year's winner is Cyril Cordor. The Outstanding Graduating Senior Award. This award is given to a student or students graduating in May or August who have shown the highest level of academic excellence in mathematics based on grades, coursework, and awards. This year's winners are Charles Devlin, Stephen Jacina, Jae-yoon Kim, and Jason Yu. Finally, the Wirt and Mary Cornwell Prize. The Wirt and Mary Cornwell Prize in Mathematics was established to be awarded to a student at the University of Michigan who, during the previous 4 years, shall have demonstrated the greatest intellectual curiosity and given the most promise of original study and creative work in mathematics. There are 2 winners annually, 1 graduate and 1 undergraduate student. This year's undergraduate winner is Annie Shu. Again, congratulations to all of you and all the best for the future.
So thank you for attending the 2020 awards ceremony. I think that at this time we should give all of our awardees a round of applause. At this point, we would usually leave the Psych Auditorium and go over to the East Hall atrium to enjoy punch and coffee and cookies and cake and all kinds of wonderful things. Since we can't do that today, I encourage you to, get your favorite beverage, mine's milk today, and maybe get some cookies and enjoy and have a good summer.